Hello everyone. So we're gonna do here a quick flyover of linear algebra. So that's a book I wrote recently that covers basic math, vectors. These are like the prerequisites before you learn linear algebra. You gotta know about functions. You gotta know about basic trigonometry. So if in case you don't know, it's good to check out this chapter. And we kind of discuss vectors and vector applications a little bit, but then the linear algebra starts. So that's what we'll look at today. Basic definitions and operations. Vector operations. Okay, I didn't want to do that. In future videos, we can cover computational stuff, geometrical, linear transformations, which are like vector functions. So kind of like the core of linear algebra is to understand linear transformations. So definitely a lot of talk about that. Then there's all kinds of theoretical issues with eigenvalues, eigenvectors. Things that can be complicated, but that's the power, right? I mean, there's going to be some suffering is necessary. So then there's the whole point of linear algebra is there's a lot of useful applications. Before we get to the applications and the cool stuff, we got to go through the basics. Okay, so what are vectors? What are matrices? And what are the operations we can do on them? So that's what we'll focus on today. And you don't want to see my face that much. So we'll focus on the book and the definition. So we're going to do now a few definitions for chapter 3. Let's jump to that. All right, to help us with this exploration, because I can talk and we can look at the book, but it's even better if you show is better than talk, than tell. And so I have this notebook. So a notebook, let me show you what a notebook is. IPython notebook, now used to be called IPython, now it's called Jupyter, is a way to run code in the browser. So I don't need to explain too much, but basic algebra. So this is just a tool to run SymPy. So SymPy is a computer algebra system that uses symbolic math, so you can get exact answers. So we're going to use that to go over the example. So instead of just looking at the math, we're going to see it in action, theory, action, theory, action, theory, action, and try to do that in 10 minutes, because I know everyone has a busy schedule. Now, I've been drinking coffee for the past 2 hours in order to reach a level of caffeination that we can do this quickly. So let's go. Let's do this. All right, first off, what is SymPy? SymPy allows you to, well, let me show you. So for example, 2x plus 3. All right, you got to run this thing, right? So you have an expression. You can do math on the computer. So for example, what if you say solve 2x plus 3? So this is like solving this, but we don't need to write that. Solve for x. Those is 3 halves. That's not that surprising, right? If you put minus 3 halves here, you'll get minus 3 plus 3 is 0. So that's kind of useful. But what if you have something like polynomial? Minus 6, I don't know. Minus 3 and 1, minus 3. So you have some polynomial. And normally, okay, this one doesn't factor, huh? Alright, what about this? Alright, there you go. So, standard mathematical operations like factoring, which everyone says, oh, you should know this from high school. Well, it's not that easy. I mean, I've been doing math for a long time, and if you tell me what are the factors of this, I wouldn't be like, yeah, I know them. And even if you are like that, I mean, it doesn't really, you don't need to know it that well, to be that quick with math. And these days, with a computer and using SymPy, you can just say, give me the factors. Factor this polynomial. There's a function. Instead of, whole high school, if you don't remember this, feel guilty. We don't need that. We just run it, and it tells you that these x plus 1 times x plus 3, if you do x times x would be x squared. Then you have 3x and then 1x, so it becomes 4x, and then 1 times 3, 3. So you can also, what can you do? You can do all kinds of things. Now, we're not going to discuss that too much, but before you can start using x as a variable, as a symbol in your equations, we have to do this. I'm just saying that now because you see that used in what we're about to do now, right? So chapter 3, and I already tried this video before. It was too slow because I had to type out all these things. So now they're pre-typed, so it will be a little bit easier. We can do this faster. Now, I don't know how many. It's been 7 minutes, so we better speed this up. All right, so let's see. Intro to linear algebra. Vectors and matrices. Really should say vectors and linear transformations, but matrices are the implementations of linear transformation. So as far as we're concerned, we're going to talk about vectors and matrices, but really we're talking about vectors and linear transformation. Now, never mind the details. So that's what a vector looks like, just a list of entries. So the dimension of the vector is how many entries there are. So this is a three-dimensional vector. You can say a vector is a list if you want, a list of coefficients, but it's not, usually it's a fixed length. A vector is a vector. Wow, super definition. A matrix is an array. Think of a table, like Excel. And you have Excel, you have letters and numbers. Here we have just numbers. We have here the first index tells you which column, tells you which row, and the second index tells you which column. So A11 is the first row, first column. A31 is the third row, first column. And the dimension, this is not super standard, but the dimension of a matrix is, we denote it with its real coefficients. These can be any number. Any number can take this place. And it's a 3x2 matrix. All right, so let's see that in code. Here's an example. All right, so what's going on here? This is standard thing, so we start using SymPy, we define some variables. This is really cool, is that equations will start to come out as LaTeX code, so everything will look pretty. And we'll also do some plotting, so I've imported some useful functions here for plotting two-dimensional vectors, so we can visualize what's going on. All right, so that's a vector. All right, so a little detail. So in math, you can say this is a vector and this is a matrix, and they're different type of objects. But really a vector, if you look at it, it looks like a 3x1, 1x3 matrix, right? The vector is kind of a special case of a matrix. So in SymPy, they don't have a special object for vectors. They use the matrix. So here I'm saying it's a vector. But why I know it's a vector is just it has, just put a list of entries, right? Now, this is, you could probably do this in any language, and in any computer algebra system, MATLAB, Octave. But SymPy is a little bit better than that, because it allows us to really treat the coefficients as arbitrary variables, so symbols. And this is kind of cool, because we can actually see the formulas. Instead of just showing examples with numbers, we can see the general formula. So that's a vector, that's a three-dimensional vector. Here it's not clear, it looks like a row vector. But since we're using matrix object, we have two types of vector. This is called a column vector, and this is the transpose of it. It is a row vector, so that looks more like this. Well, as far as we're concerned, we don't care the shape. We care that it has components. So this is the first component, second, third. Here's first, second, third. That's vectors in general. We're going to study that for whole course. These will be the inputs and outputs of functions. So that's linear algebra. We also have matrices. So here's an example of a matrix. So that's a 3x2 matrix like this one. If I don't make mistakes when I'm typing. I just picked some random numbers. All right, so that's a 3x2 matrix. Again, we can do the same thing with symbolic matrix. So that's a bit wordy, but it's worth it. So we have defined 6 symbols, and then we build a matrix. So notice the syntax for creating matrices. It's a list of lists. So each list is one row. The outer list represents the columns. I cannot point, right? And then the inner list represents each row. Same thing with symbolic. So that's the two objects. We're gonna go switch back to the book. All right, it's been 12 minutes. We gotta speed this up now. Speed it up. All right. So in the book we say what can you do with vectors and matrices. So it's good to review. So we have addition, subtraction. That's when you change multiplying a vector by a constant. And then we have two types of products. So these are pretty intuitive. These are just normal. Whatever you're used to doing addition for numbers, you can now do addition, subtraction for vectors. These will take some getting used to. So that's why we're going to look at this. Similarly for matrices, we have addition, subtraction, multiplication, standard things. And the matrix product is really weird. So we have to take a look at that a little in more detail. Then we have some other matrix-specific operations which we'll look at. That's an interesting effect here is when you mix matrix times a vector. So if this simple equation is extremely powerful. So when you look at A, the 3x2 matrix, X is a 2x1 vector, so a column vector. And the way this is defined is you take the first column here times x1, and then the second column times x2. You can write that down. So this will be a 3x1 vector output. You can write it down as follows. So you see it's x1 hits this one, then x2 hits this one. So really useful matrix vector product. Really useful. We'll talk about that for many things. most importantly, vector functions. So linear transformation, I said this is what the book is about. This is a little intro, which we're not going to go into. This is lagging. All right, vector operations. Vector operations. So let's define some vectors, u and v, with coefficients 1, 2, 3, and a constant alpha. So this just defines these things. Let's see u. What does u look like? It looks like a vector. What is alpha times u? Well, guess what? Alpha multiplies each of the coefficients. This is the sum of u and v. The coefficient, the first coefficient is the sum of the first coefficients of u and v, and so on for the others. The norm, also known as the length of a vector, is equal to, imagine you have like the three components, and you're doing it's basically Pythagoras theorem, tells you the length of the vector. Right. So let's see, insert below. So that's this picture here. We define a vector 1, half 1, and then this is the vector 2 times that. So that's the cool part about vectors, especially in 2D and 3D, we can actually show them as arrows and have a geometrical intuition about vectors. So this is just an example of, probably should add it here. But anyway, you get the point. Now, dot product. Vector multiplication. So there's a dot product and cross product. So the dot product takes two vectors and tells you a number. The cross product takes two vectors and produces a third vector. This is called the algebraic formula. So you take each of the coefficients of u and v, multiply them together, and take the sum. Kind of more fun. Let's see this. So you have two vectors. This is the first one. So when I use this plot vectors, the first vector is always going to be black, and then the second one will be blue. So this is u and this is v. And then I say, what is the dot product between u and v? And tells me that it's equal to 3. So what does that mean? The dot product, look at that. The black vector, the amount of the black vector in the direction of the blue vector is this. And then we do 2, 3. So it's not like the product of their lengths, but it's the product of how much of this vector is 1 times the length of the other one. Really useful operation. This will work a lot with that in this course. Once there is this angle here, which is 45 degrees, and we can obtain that angle. Well, let's just say this. If you knew this angle, then the dot product between them will be the length of the first vector times the length of the second vector and the cosine of the angle between them. And you can use this fact to compute the angle between them. So if you use the function in the opposite direction. Right. Anyway. Dot product, useful for, basically the intuition is how similar are these two vectors. So two vectors that point in the same direction will have a big dot product together. Two vectors that are perpendicular will have 0 dot product together. So that's kind of. Now what about the cross product? So the cross product is a weird mix. Look at that. So if I take an arbitrary u vector and a v vector, so the first component of the cross product contains a mixture of these coefficients. The second one mixes this one, and the third one. So it's a weird mix, and if you've never seen a cross product before, it's something to get used to. The cool part about it is the geometrical intuition. So if this is the first vector, u, all right, this is the u vector, this is the v vector, the cross product of the two, of u, the cross product of u and v, is a vector that sticks out perpendicular to these two. So that's really useful when you want to find things that are perpendicular. So this dot product is useful when you want to find the part of vectors that are in the same direction. Cross product useful when you're finding orthogonal vectors. Another way so the cross product is a vector, but the length of the cross product can be obtained again in terms of the length of the individual vectors and sine of the angle. That's interesting. The dot product was the cosine of the angle. The cross product, the length of the cross product, is with the sine, cosine. So yeah, All right, moving on. Okay, it's been 22 minutes. Ooh, better be watching this video on 2x. So projection. So dot product, very useful for computing projections. So the projection of a vector v in a given direction is given by the dot product, where a direction is a unit length vector. In general, if d is not a unit length vector, this is the formula. So let me run this, and then I can show you with a picture, and then explain the formula. So I say, give me the projection. So this is a standard thing. We have a direction here in blue, and we say how much of this black vector, what is the projection of the black vector in the blue direction? And the answer is the green vector. So, you know, it's the blue, just, we don't care about the length of the blue. Blue could be short, it could be even super short, could be long, could be even, it's just the direction. So we just want to specify that. We care about the length of the black vector. Specifically, we care the part of the black vector in that direction. So this occurs so often that it's good to have a function we can call whenever we need that. So that's the projection. So the projection of vector d in the direction d. This is the formula. You do the dot product between the vector and the direction divided by the length square of the d, and multiply times d. So the best way to understand this is here. If d was a unit length vector, it would just be the dot product times d hat. In general, if you have d is a non-unit length, you can make it a unit length by dividing by its length, so like this. So this formula, that's what we've programmed here. Take the dot product, divide by the norm, times, this is just going to be a number, times this vector. We've made d into a unit length vector. So this is the example from where we're looking at. That projects projection of u onto the direction v. So if I change this to 40, right, and we could change it to 400, it shouldn't change the projection, right? So we only care about v here is the direction it's in. So in particular, look, this is a super short v, and it goes that way. So in fact, crazy as it may be, you can put negative, right? We don't care about, it's just an axis. We don't worry about it. All right, so let's put back 3, because our vectors go up to 3. Now you have it. So that's a projection. Really important, really important. All right, and we're done with vectors. That's it. These 5, 6 operations, the dot product, cross product, addition, and length, is everything you need to know about vectors. I kid you not. It's an entire course on linear algebra that if you understand these operations, you're in good shape. If you don't, then we have a problem. You have a problem. I don't have a problem. I don't want you to have a problem. So you can use SimPy. You can review them on paper and really make sure you understand vectors. Next, matrices. Stop doing this. Matrix operations. So, right, 2-dimensional arrays of numbers. So m by n matrix has m rows and n columns. This is a 3 by 2 matrix. And if you add it to another, let's run this. So this is what A looks like. Again, we just define symbols for each of its entries. The sum of A and B looks about the same, is the sum of each coefficient. Right? If you have an array and you have another array, say plus, it makes sense that you add the top left entry with the top left entry of the other one. You can also multiply matrix by a constant. Guess what happens? Each entry gets multiplied by that constant. All right, recall the matrix vector product. So this is really, really, really important. So A is this matrix here, and we're hitting it with the vector, with the column vector v1, v2, exactly like we're seeing here. What's going to happen is the output of this is a 3 by 1 vector. And you can say it's equal to this times v1, this column, plus this column times v2. So it's a linear combination of the two columns. It's called the column picture. Another way to think about this matrix vector product is, say, this vector and this vector, you're computing the dot product and putting the result in the first entry. Whether you choose the column picture or the row picture, it doesn't matter. In the end, you get a 3 by 1 vector which contains this in its top entry. Why do we define it like that? Well, it's a special kind of, this is the matrix, this is how matrices are multiplied. I mean, we define matrix multiplication, matrix vector multiplication this way, because computing linear combinations of columns is a really useful thing to do. Computing dot products is a really useful thing to do. So that's the reason we have this. So this is a weird Python notation. This is not standard math notation, but it's kind of important. Let me show you here. When you say dot, normally you can access individual entries by saying like the 0, this is a top left entry here would be 0, 0. But if you want to see the whole column, you put column like this times the 0th entry of the vector times this is the second column of A. So you say all the i's, all the rows in the second column times the second coefficient of V. So that just to show like this, that's what it means. It doesn't mean multiply each entry of A times each entry of V. That's, you know, if you're adding vectors, adding matrices, you add them component-wise, but the matrix vector product is completely different. Here is the general formula for multiplying a matrix times another matrix. This is a 3 by 2 matrix times a 2 by 2 matrix. There's a condition. If you want to multiply two matrices A and B, they must have the same inner dimension. So this is 3 by 2 times 2 by, so it's okay because this 2 matches this 2. And you can imagine each row here and each column and each entry here contains the dot product of the ith row and the jth column. That's how much I'll say to that because we want to skip. It's just, that's the way matrix product is defined. I'm not going to explain why. We have a whole book ahead of us that will talk about it. So that was the matrix A. The transpose operation, denoted AT, is the same entries, but now we flip them. So if this was the matrix, when you flip, well, this is the opposite here. The first column of A, when you do the transpose, becomes the first row. So a 3 by 2 matrix became a 2 by 3 matrix. So for any vector, for any matrix, you can ask what is its shape. So V, which we defined up here, is a 2 by 1 matrix. So it's a column vector. The transpose will be 1 by 2. It's a row. So 1 row, 2 columns. This is really off topic, outer product. Right. Well, let's talk about the inner product. V, U times V. So imagine U is a you can make a column. Oh, okay. Focus, Ivan. A row vector U times a column vector. So the way matrix vector product is defined, if you have a row vector times a column vector, what happens is you get the dot product. So you can either say U and V, think of them as amorphous vectors, and say the dot product, or you say no, U is a row vector, it's a matrix, a 1 by 3 matrix, and V is a column vector, a 3 by 1 matrix, and you say matrix product between the two of them. And the matrix product will be also known as the inner product, or dot product, whatever you want. It's the same operation, you get the sum of the products of their corresponding entries. Now, the outer product is the opposite. You take this times this, it goes in the first entry. Really off topic, really off topic. It's kind of a cooperation, we're just going to skip ahead. Now, let's see an example of, concrete example of a matrix. So that's the matrix 3, 3, 2, 3 halves. Side note, I had to do this because if you do 3 halves, it would be a float. Yeah, the little details, don't worry about it for now. So that's a matrix. This is the inverse matrix. So the product of the two matrices, that's sort of the definition of the inverse matrix, is when you do the matrix times its inverse, you get, what do you get? You get 1. But 1 in matrix land is a matrix which has 1s on the diagonal. It's called the identity matrix. If you do it in the opposite order, you still get the identity. So it doesn't matter if you do A inverse or inverse AA. This is, when we learn about matrices as like operators acting on vectors, you can think of this as the inverse operation of A. So if A acts on vector, then this will undo the action. So together they have this called identity. So it does, whatever V is, it comes out unchanged. All right, and the last two, we have trace and determinant. So the trace of a matrix is the sum of the entries on its diagonal. So here is a matrix B. So this is its diagonal, and the trace is the sum of this entry plus that entry. Why is this useful? Well, you'll see, it turns out it's a property of the matrix. It's important to know what's on the diagonal. So here's a matrix. It's a special operation defined for any matrix, any square matrix. It tells you what's on its diagonal. Then you also have determinant, which takes this entry times this entry and subtracts this entry times this entry. You write it either as a function, as an operation that acts on a matrix. Very often people just write it as straight lines, so don't be confused. This is a matrix, whereas this is a number. This is telling you to do the determinant operation on this matrix A, B, C, D. So if you do it on this matrix B, it's going to be this times this minus this times this. Better be. right? So the main diagonal minus. It becomes more complicated as an operation when you do 3 times 3. So, but let's not get ahead of ourselves. A whole chapter, a whole section in chapter 4 that discusses determinants. And with this, we're done. That's what I wanted to show, the basic operations of linear algebra, and vectors and matrices. So the good news is, the bad news, I don't know how you feel right now, but there's a lot of stuff to learn. If you've never seen these operations, you will have to get used to them, and you'll be expected to like do them very quickly. The good news is we've seen it all. Nowhere in the remainder of the book will I show some new operation that we haven't discussed in here and be like, oh, you should know this. You know, like that's what we do in linear algebra: vectors and matrices and determinants, traces, all these things, row operations, mix of columns and rows, all these things. We've just seen them, right? So that's it. That's it. I mean, this was maximum exposure to all the stuff that has to come. So this is an extremely important property called linearity. So this is what we define as a line-based linear function. But that will be for another video. Today was all about the definitions and a little bit of SymPy. Hope you enjoy. You can get the notebooks at here. No BSN notebooks. So this file will be here shortly, chapter 3, definitions. All right, peace out.